So since we have begun working on optimization problems in calculus this week, I thought it would be worthwhile to do an example video so that you all can refer back to this if you get stuck on your own homework. So the situation is the following. Pappy Joe Jim Bob raises American bison to sell for their meat and hides. His business has been booming so much that he needs to expand. He is planning on creating a new pasture next to his current larger pasture to increase the amount of pasture available for grazing. He has stipulated one side of the new enclosure will utilize fencing that is already in place, so he only needs to build 3 sides of the rectangular enclosure. Okay, so that's pretty important. He only needs to build 3 sides of the rectangular enclosure. So we know the shape we're working with. We know that we only have to worry about 3 of the sides of the rectangle. Pappy Joe Jim Bob has hired you, since he knows you are taking calculus and can help him. Use your skills of calculus to determine the dimensions of the new pasture that will maximize the pasture's area while using no more than 500 meters of fencing. So this is the key information that we need here. So let's see if we can get a picture drawn of this. Let's see, I think I want purple. So we've got some sort of a rectangular enclosure which is up against a fence that's already in place. So here is the fence that's already in place, and on that I'm going to make a rectangle. Whoops, that's not what we want. On that I'm going to make a rectangle. Okay, so here is the rectangular enclosure, the new enclosure, and the sides that we are worried about will be this side, and this side. Not the prettiest picture, but hopefully that gives you the idea. So let's get some labeling done. We don't know what any of these dimensions are, but we do know that we're looking to maximize the area. And how do you find the area of a rectangle? Well, that's length times width, or in this case, the way I'm labeling it, x times y. So we need to maximize area. The other thing we know is that the amount of fencing that we're going to use is 500 meters. Now, since we're leaving off one of the y sides, we're leaving off this side, we don't have to build a fence here. That means that 500 meters must be equal to 2x plus y, because this length is x, as is this length of x, plus the y. Okay, so we now have 2 functions. Since we have 2 functions, and they each have 2 variables, x and y here, x and y here, I can rewrite one of the functions in terms of x or y, plug it into the other function, and then use our first derivative test to figure out the the dimensions that will maximize the pasture's area. So I'm going to isolate y in this equation. That looks easiest to me. So that would be minus 2x on both sides, which will give me y equals 500 minus 2x. Now that I've solved for y, I'm going to plug it into my area function for y. So I'll have x, which is this x, times y, which we determined we could rewrite as 500 minus 2x. Okay. So let's go ahead and distribute this out, just so taking our derivative will be a little simpler in a minute. 500x minus 2x squared. And now we have one function in terms of one variable, which we can take the derivative of. This is a pretty simple function, and then use our first derivative test. So let's do that. So the derivative of a, or a prime, is equal to 500 minus 4x. All right. Now that I have my derivative, I can set it equal to 0 so that we can find our critical values for this particular function. So we'll see here that 4x equals 500. So x equals 500 over 4, or 125. Now that's one critical value. We know that we can't have a negative dimension for a fence. So we know that the domain of this particular function here, if I make a note, domain would have to be x being between 0 and 500. Okay, so the domain would have to be x in between 0 and 500. Now if we make a rectangle that's got a side length that's 500 meters, that doesn't leave anything for the other side, so you wouldn't have a rectangle. So in this particular case, since we've only got one critical value, that tells us that the side length for x needs to be 125 meters on both sides for x, 125 meters here as well. And since we know that our perimeter, the total perimeter, had to be 500, or in other words, y has to be 500 minus 2x, that's going to give me 500 minus 2 times 125 equals y, or 500 minus 250 equals y. So y, therefore, is equal to 250 meters. I hope this problem, while it is a more basic optimization problem, gives you an idea for how to go about tackling these optimization problems. You're going to need at least two functions. You're going to need to write one of those functions so that it is in terms of just one variable, which means that you'll need to solve another function to isolate a variable like we did here for y. We isolated y so that we could then plug into our area function. So this was our y. Then go through, find your derivative, set it equal to 0, find your critical values, test those, and sometimes your endpoints, depending on the type of the situation. In this case, we didn't test our endpoints because they wouldn't have made any sense. You can't have a rectangle with 0 dimension. But if we were talking about cost, for instance, if this was an economic problem, you could have a cost that's equal to 0. So that would make sense to test. And then test whatever values make sense in this particular situation to determine your maximum. So have we answered the question here? Did we determine the dimensions of the new pasture that maximize the pasture's area? Yes, we did. They should be 125 meters by 250 meters. Hope that was beneficial. I'll see you guys in class soon.